So in this video, we're going to talk about a solution to the subset sum problem. So as you have already seen in our last example, the solution to a given subset sum problem is really not that obvious, especially when there are a lot of items in S. And that is because in those cases, the number of possible subsets are really, really big. So how do we find a solution? If you want to think about it on your own, pause the video, think about it a little bit. Otherwise, continue watching. I'll give you some hints. So most of the solutions, there are many different solutions to the subset sum problem, but most of them, or all of them as far as I know, involve generating all possible subsets of S, right? And then after that, we just figure out the sum for all of them and then find the subset with the largest sum that is still less than or equal to the target. Now, there can be multiple subsets with the largest sum and still less than or equal to t, but we only have to find one for our purpose. Okay, so let's start with our small example again, right? S with 10, 2, and 8. What are all the possible subsets of S? So pause the video, find all the possible subsets. And here is the answer. There are 8 subsets for this particular set of items. Now, these subsets, these 8 subsets are written in such a way to give you a hint on how we can actually systematically generate all subsets of S. So, can you then come up with a systematic way of generating subsets of S, regardless of how many items are in S? Okay, so one way to do that is that, let's say for a given S, we already know all the possible subsets. Now, if S is expanded by one item, we call it X, so that it becomes S becomes S prime, right? And then all the subsets of S prime would then include all the original subsets of S, as well as all the new subsets that we can obtain by adding the new item X to each one of them. Okay, so that's a mouthful. If you can understand this statement, great. If not, you can continue to watch and we'll show an example of that. All right, so let's say we start with an S that has nothing in it, right? That is the most basic case. So if our S has nothing in it, then the subset of S would be, well, just the empty subset. Okay, next step. Now, S has one more item in it, the number 10. Now, what the previous algorithm tells us what we should do is, well, now the S, one of the subset is indeed still the original empty subset from the previous S, right? Now, we should also duplicate the original subsets. So now we make a copy of the empty set. And then in these new subsets, we add the new item. Okay? So these two subsets are now all the possible subsets of S that has a single item in it. Okay, we have to repeat this process. Now, we are expanding S by another item, in this case 2. So the subsets of S obviously include what was there before, and we make a copy of them. These are the new subsets, and we just add the new item to these new subsets. So now all the subsets of S, there are 4 of them showing here. Okay, so what if S is expanded again? Now we're adding an additional number 8 in it. Well, the same thing happens. We keep the original subset from the previous S. We duplicate all those subsets, and we add the new item 8 to each of these new subsets. Now we have 8 subsets for the expanded S. Okay, so I just kind of want to point out that the number of subsets of S grows very fast, right, as the size of S increases. So, which is why it will take a long time to quickly find the solution for when the number of items in S is very large. And we will very soon study this in more formal terms. So now it's your turn to try to use the algorithm I just described to generate all the subsets for S, that is 1, 2, 3. Okay, I hope you get the same thing that I got here. And then now let's make S a little bigger. It contains 5 items. And then again, go through the same algorithm and write out all the subsets of S. And yes, this will take a little bit of time. And assuming you have done that, here is the answer. There are, I believe, 32 subsets for this S. Okay, so now that we kind of conceptually know how the solution works, let's have the formal solution written in pseudocode. Now, before we can present a solution, let's have some, let's get some definitions out of the way. So one of the things we'll need is that if L represents a set of positive integers and X is just a single one, then when we say L plus X, it really means this is a subset that includes all the integers that was in L and also the new integer X. So here, if L is 10 and 2, X is 8, L plus X is 10, 2, and 8. All right, that should be pretty straightforward. And what does sum L mean? Well, sum L, it just means the sum of all the elements in L. Okay, so if L is 10 and 2, then sum of L is 12. Right, pretty straightforward. And finally, we need to have something col, C-O-L, that represents a collection of subsets. So let's say if S, as we already just saw, if S is 10, 2, and 8, then col may be, these 4 subsets. Now, col doesn't necessarily mean all of the subsets of S, right? It could be all the subsets, or could be just some of the subsets. So, but again, the important thing to remember about col is it's just a collection of subsets. Okay, and here is the formal solution written in pseudocode to the subset sum problem. I'm not going to read through this. I want you to read this yourself and make sure that you really understand it. But this pseudocode here basically describe what we just saw in our example, how we generate all the possible subsets. Okay, so read this, please. Now, there are a couple of things I want to point out about the pseudocode that are kind of subtle, and is something that you should pay attention to when you implement this in the assignment. So the first thing is this calls for iterating or looping over all the subset L that are already in code. So we're iterating through all the subsets in code, and then we're also adding new subsets to code. So what's happening here is, code is changing while we're iterating through it. So it's important to understand that when we're iterating through code, we're iterating over all the original subsets in code. We're not iterating over the new ones that are being added to code in the process. So that is something very important to keep in mind. And then the second thing is that, when the sum of the new subset is T, we break, we get out, because we find our subset that we're looking for. Now, this break is kind of an optimization. It's not strictly necessary for the algorithm's correctness, but it's a very good optimization, because the chances we'll hit this case before we kind of exhaustively search all of our subset. Okay, so that's really the solution. Hopefully you understand it by now. Before I leave this problem, I just want to point out that the subset sum problem is in fact a special case of what's a general class of problem called the knapsack problem, and there are wiki links to them if you're interested. And it's one of the what's called the NP complete or NP hard problems. NP, if you're wondering, it stands for non-deterministic polynomial. So these problems, whenever you hear the term NP complete or NP hard, they represent problems that are very computational expensive, because the solution just takes a lot of time, and this time is what's called exponential time, and that's at least, the real solution always takes exponential amount of time to compute. Now, what exactly this means, we will study in I think in a week or two.